Hi everyone, I'm Mo.
And I'm Yuval.
First, thank you for inviting us to the conference. We're very excited to be here. We're both graduate students studying computer science at Tel Aviv University. In this talk, we'll discuss some recent advancement in StyleGAN and the powerful thing that we can do with it. A lot of this talk will focus on a task called inversion. How can we encode real images into StyleGAN's latent space? But along the way, we'll show that there is much more that we can do with StyleGAN, whether it's wide range of image-to-image tasks, such as generating realistic images from sketches, or image editing, where we can control, say, hairstyle or age. So let's get started. We're going to talk about generative models today. As we assume that you all know, generative models have made a huge progress during the last years. As you can see here, the quality of the generated images has improved dramatically from the seminal work of Goodfellow to the amazing quality that can be achieved today. The state-of-the-art GAN is StyleGAN, and as you can see, it can generate very high-quality images, which are almost indistinguishable from real images. Apparently, as we will see soon, StyleGAN is much more than just a great generator. It also has interesting properties, which we will see next. Like any GAN, StyleGAN receives as input a latent code Z, which is sampled from a normal distribution and generates an image. There are two key differences between the architecture of StyleGAN and previous generators. First, StyleGAN has a latent space, which is called W, in addition to the standard latent space Z. The special thing about W is that it is a learned latent space. Part of the architecture of StyleGAN is this mapping network, which maps the normal distribution of Z into another distribution. Because this mapping network is trained, the distribution of W naturally fits to the distribution of the real data. As we will see soon, W has special properties like disentanglement. The second difference is the injection of the latent code into the network. Unlike other GANs, in StyleGAN, W is inserted into the network through style modulation layers. As we will see, in each layer, this latent code or style code controls different levels of details in the image. To sum up, the generation begins with a latent code Z, which is sampled from a normal distribution. It is then mapped into some latent code W, and then it is mapped into some latent vector W, and finally it is inserted to the generator through style modulation layers to generate the image. Let's start to talk about the disentanglement properties of StyleGAN and for what it can be used besides generating amazing images. In this image, you can see that the latent code that is inserted into different layers control different level of details in the image. The W's in the first layers control coarse level of details such as gender, pose, and age. In the medium layers, it controls medium level of details such as eye shape and expression. And in the last layers, it controls fine level of details, mainly the color scheme. This shows the disentanglement between the layers of the generator. Let's start to explore the W latent space. It has been shown that by performing latent space traversal, we can achieve semantic changes to the image. For example, if we have some latent vector W that corresponds to some image, we can go on certain paths in the latent space and obtain semantic meaningful edits. For example, here you can see that some paths that correspond to changing the pose or the age. This brings us to one of the most common usages of StyleGAN, image editing. So there are a lot of methods that propose different approaches for editing using StyleGAN's latent space. As you can see, it is possible to edit age, to add eyeglasses, to add wrinkles, or change the expression. Observe the quality of the images and note that all these manipulations are done when the generator is frozen. By changing only the input, we're able to achieve these results. From now on, our generator is always going to be frozen unless we say otherwise. So a natural question to ask is how to use these amazing image editing capabilities for real images, like this image of Obama. To perform all the manipulations we've just saw, it is necessary to know the initial W. So to edit a real image, we must find its corresponding W, such that in inserting this W into the trained StyleGAN will reconstruct the image. This process of finding the latent code that reconstructs the image is called inversion, and it is not new. It was actually proposed even before StyleGAN. A simple technique to invert an image is to optimize the latent code. So we can start from a random guess, insert it into the pre-trained StyleGAN, obtain the corresponding image, compare it to the target image, and update the W through some optimization algorithms such as gradient descent, for example. If we keep doing this process, we converge to some point in the latent space. But as you can see, the result is not good enough. A previous work called Image to StyleGAN concluded that W is not expressive enough to represent any real image. Their solution to this problem was to extend the latent space. Recall that in the original architecture of StyleGAN, we insert the same latent code W into all the layers. They proposed to extend the latent space by inserting different latent code into different layers. For example, in the case of human faces generator, where there are 18 layers, we have 18 different Ws. They called this extended latent space W+. So let's see how this latent optimization works in W+. So again, we can do the same process of beginning with some latent vector W, insert it into the pre-trained StyleGAN, obtaining an image, and the same update as before. And now we converge to a much better reconstruction. But the problem with this optimization approach is that the optimization is too slow and can take several minutes per image. A different approach for inversion is to train an encoder. An encoder takes as input the image and returns the latent code W+ that reconstructs the image. This approach is fast because at inference time it only takes a single forward pass, but it is not so easy to get a good reconstruction. So we have a dilemma between optimization and encoder for the task of inversion. As we will see next, there are more trade-offs besides the inversion time and the reconstruction accuracy.
So thank you all for that great introduction. And now we're going to talk about our first work called Encoding in Style, a StyleGAN encoder for image-image translation. And this is really our first work that O and I work together in the world of StyleGAN. So this is really where our journey begins. And in Encoding in Style, in this work, we propose a new encoder for StyleGAN inversion. But beyond this inversion task, we've shown that StyleGAN in our encoder can be used to benefit many different applications for image to image. For example, in painting, sketch to image, and super resolution. And we called our encoder pixel to style to pixel, or PSP for short, because we start with an image, we're going to encode it into its latent representation, and then return a new image that corresponds to the transformation that we want to attain. And the training of the encoder goes as follows. We'll start with the image. We'll pass it through our encoder, which we'll see the architecture of it in a minute. We'll get this latent representation and insert it into our StyleGAN to get the final reconstruction. Now, note that when we train our encoder, okay, using a set of losses that we'll see in just a bit, the StyleGAN generator will remain fixed. Okay, and we'll only learn to train the encoder network. And this is important because it means that there's no adversarial training required, so there's no discriminator, and the training scheme is quite simple. All we'll have to do is train the encoder. So what is this encoder? How does the architecture look? So motivated by the hierarchical structure of StyleGAN with the coarse, medium, and fine layers that we saw earlier, our encoder is based on a FPN, a feature pyramid network, where we're going to extract features from 3 different levels, corresponding to the fine, medium, and coarse layers of StyleGAN. And what we'll do is we'll pass each of these W vectors that we'll extract from our encoder into our fixed StyleGAN generator. And the set of losses that we're going to use to train our encoder, we're going to use some simple losses that were commonly used before PSP, such as L2 and LPIPS, a sort of perceptual loss. And in addition, we're going to introduce 2 different losses, a regularization loss, which makes sure that we encode images into well-behaved regions of StyleGAN, StyleGAN's latent space, that is. And the most important loss that we found when working on the facial domain is this identity loss, where we're going to take a pre-trained facial recognition network and compare the facial embeddings of our input image and the output image. And this forces the encoder to preserve the identity of the individual. Now, let's see some of the results that we get with PSP. And these are the results, and actually it's kind of strange to look at this after a year and a half. but at the time, this was actually the state of the art for StyleGAN inversion. It's important to note that when compared to optimization, PSP runs in a fraction of a second in about 0.1 seconds per image. So it's quite practical for real and interactive applications. And just to give you an idea of where we stood between previous approaches for encoding-based inversion, we have ALE and ID invert. And we can see that we're able to, much better preserve the input identity of the individual that we see here. But let's go beyond the inversion task and see how we can use our encoder to perform various applications. So first we have this invert and edit approach, where what we're going to do, a common application for inversion that we saw earlier was editing, right? So what we'll do here is we'll take our image, encode it using our PSP encoder into W+, find a direction that transforms age, right? Using the approach that we saw, a latent space traversal, and then pass it to our pre-trained StyleGAN to get the edited image of the same individual at a different age. And this works great for images that we can encode into the latent space of StyleGAN. But we asked ourselves, what about other image-to-image tasks? For example, what if I wanted to take this sketch image that we see here and transform it into this realistic image on the right? Here, the problem is that I can't simply encode the sketch image into StyleGAN's latent space because StyleGAN never saw something like this during its training, right? The sketch image doesn't appear in the latent space of StyleGAN. So how do we do this? How can we perform this image-to-image translation? So our key insight here was that we can actually encode our sketch image using a sort of translation, a translator, into a desired latent code that corresponds to the desired output image that we want to attain. And this allows us to transform images, an input image and an output image, that do not reside in the same domain. And now, since we use the pre-trained StyleGAN generator, right, we are able to easily leverage its amazing image quality. Right? And the training scheme is almost identical to the inversion training scheme that we just saw. Now, all we have to do when training our translator is compare not the sketch image to itself, but rather the output image that we get to the right with the original ground truth image. And now we're going to see a bunch of different applications of image-to-image translation that we can solve using this direct encoding approach. So in a sense, PSP is actually a generic framework where we're able to solve a wide range of tasks all using the same architecture and training scheme. And this is quite different than previous approaches for image-to-image translation, which typically designed dedicated architectures for solving a single task, for example, super resolution. But here we have the same framework for solving a wide range of tasks. So let's see what we can do. So first, like we just saw, sketches. And we can transform them into realistic images. And by leveraging StyleGAN's rich latent space, we can perform style mixing on the fine layers of StyleGAN to generate images of various color schemes. And this is multi-model support is given for free because we're leveraging StyleGAN's power. Similar to sketches, we have semantic segmentation, segmentation map to a real image. And same idea here, we can apply style mixing to generate an endless collection of output images for each input image. We have super resolution, where we're going to generate a high resolution image for some low resolution input, and much more from in-painting to image tunification to sketch-based local editing. And again, all the things that we see here are all done using the same architecture and training scheme, with minimal changes to the loss functions. And since the release of PSP in August of 2020, we've been quite amazed at the things that we've seen with PSP in the community. We have various videos with over 1 million views describing PSP and the things that we can do with it. We have a bunch of different posts on Twitter with people playing around with different things that we can do with PSP. And I think one of my personal favorites is that one of the things that someone did with PSP was actually make a meme, which is not something that you see every day. So this is really, really cool to see. So we've seen that with inversion into W, where we have different inversion methodologies, And when we invert into W, we're going to get this great editing capabilities, right? Because we have this good latent space of StyleGAN, but the reconstruction is not going to be quite accurate. And if I invert Obama, say, and the inversion doesn't really resemble Obama, then the edits I will apply afterwards are quite meaningless, right? They're not too useful for me. In addition, we saw optimization, right, which gives us near perfect reconstructions of the input image, but because they take several minutes per image, it's not very scalable. It's not very useful for interactive applications. And as we just saw, we have encoders into W+, where we get near real-time inversion, but they only give us an approximate reconstruction, right? There's still this gap between optimization and encoders. Okay, so it seems like we're kind of stuck. We haven't really answered the question of whether to use optimization or whether to use encoders. So my next question is, can we try closing this gap? More specifically, we asked ourselves, what if we can give the encoder a second chance at inverting the image? And this leads us to our next work, Restyle. And in this work, we're going to take existing encoders such as PSP and introduce an iterative refinement technique to improve their inversion. And I'll talk just a bit what I mean by this iterative refinement, but our hope is that by using this refinement technique, we'll be able to obtain much more accurate reconstructions compared to existing encoders, but at a much smaller cost compared to optimization. In a sense, closing the gap between these two techniques. Let's go back to our typical encoding scheme that we saw earlier with PSP. What we'll do is we'll take our original image, pass it to our trained encoder to get our latent representation E of X, and pass it to our trained StyleGAN generator to obtain the output image Y out that we see here on the right. But as you can see, there's still a lot of room for improvement. So with Restyle, we're going to do something a bit different. What we're going to do is we're going to start off with some initial guess for the inversion of X, which we'll call W0, with a corresponding image Y0 that we see here on the left. Now, what we'll do with Restyle is we'll take our image X and the image Y0 and pass them together to our encoder. Now, rather than asking the encoder to directly invert the image X, we'll ask it to predict a delta 1 with respect to W0. Now, we'll sum these two latent representations up to get our new inversion prediction W1, which when passed to StyleGAN will give us the output image Y1. But so far, there's nothing new here. And this is where the iterative refinement will come into play. What we're going to do is we're going to pass Y1 back as input to our encoder in the next iteration and set our current inversion prediction to be W1. Now, in the next iteration, we're going to take X and Y1 and pass them together to our encoder to obtain a new delta 2, now with respect to W1. Summing delta 2 and W1 will get our new improved inversion prediction, W2, which corresponds to our output image, Y2. And we can already see, after just one more step, we're able to obtain a much higher quality reconstruction. Now, with Restyle, we're going to repeat this iterative loop a small number of times, say 5, and we're going to gradually improve our inversion prediction. Now, training Restyle is very, very similar to training PSP. We're going to have a large data set of images, and in each training batch, we're going to perform these 5 iterative steps, where in each step, we're going to compare our output image with the input image, compute the set of losses, and perform backpropagation in order to update our encoder, all while the StyleGAN generator remains fixed. And after training, the inference is exactly the same. We're going to perform these 5 iterative loops, but now since the encoder is already trained, there's no need to compute losses, and there's no need to perform backpropagation. So the inversion itself is quite easy and quite fast. It takes about half a second per image. And if I had to describe Restyle in a few words, I would say that with Restyle, we're trying to optimize. We're trying to learn to optimize, but optimize in a very efficient manner. Now, if we're going to take a bird's eye view of the latent space and what's happening with all these inversion techniques, let's consider the following example. Let's assume that this is our original image, and assume for a second that we have its perfect representation. Of course, we don't really know this representation, but let's assume for this example that we know this. Now, what we're going to do with PSP is we have a single shot of getting as close to the perfect representation as we can. But since this is quite hard to do with a single shot, PSP will be quite far from this perfect representation. And the reconstruction itself will be a bit inaccurate. With optimization, on the other hand, we're going to take many different small steps and gradually approach our perfect representation to obtain a reconstruction that is quite almost near perfect compared to our input image. And with Restyle, rather than taking 1,000 steps to approach our perfect representation, we're going to take, say, 3 steps, but 3 learned steps in order to approach our perfect representation. And our quality is going to be quite similar to that of optimization. Now, let's try to visualize the iterative refinement at play. And what we can do is we can actually visualize the step-by-step reconstructions of Restyle. And notice how we're able to slowly improve and fix the pose of the individual that we see here on the top, or the structure of the church building that we see here on the bottom. And what's cool is that it actually looks like Restyle works in a coarse-to-fine manner. And what we're going to do is we can see that in the first iteration, we're going to focus on more global aspects of the image, such as the background or the car shape. And in the next iterations, the encoder itself starts focusing on the finer details, such as the wheels or the front bumper. And this kind of makes sense because at each step, we're going to pass to the encoder our original image and the current reconstruction, so the encoder can learn where to focus its attention in the next step. Now, let's look at some of the reconstruction results that we get with Restyle. And on the left here, we have the input image, and on the right here, we have our reconstructions. And we can see that we're able to get some quite accurate reconstructions. And since we're working with StyleGAN, we're able to interpolate between these representations to see these interpolations that we see here on the video. And we can easily apply Restyle to more challenging, less structured domains such as cars, churches, and horses. And the real thing to remember here is that we're always going to use our pre-trained StyleGAN to leverage its amazing image quality and that semantic space that provides us with that editing capabilities. And just like we saw with PSP, we're trying to go beyond the inversion task to see what else we can do with our Restyle encoder. And we focused on the task of image tunification, where we're going to try to transform our real image into a tunified or a cartoon version of the individual. And we can do this with PSP, but if we take a look at the problem, we're trying to do 2 different challenging things at the same time. First, we need to encode the input identity into the latent code. And second, we need to capture that tunified style. And each of these 2 things is quite difficult to do on their own, yet let alone together. But so with Restyle, we're going to do something a bit different. We're going to propose a encoder bootstrapping technique, where we're going to split this process into 2 different stages. In the first stage, we're going to simply encode the image into the FFHQ StyleGAN, the StyleGAN generator that was trained to generate realistic faces. And at this stage, we're going to try to capture that input identity. Now, we'll take our original input and the output that we got here at the top and pass it to our second encoder, which is tasked with learning to capture that tunified style. Now, if we take these 2 representations and sum them up, and pass the resulting latent code to our tuned StyleGAN that knows to generate these cartoons, we're going to get the result that we see here. And we can notice how we're not only able to better preserve the input identity, but also capture that nice tunified style that we're looking for. But in the beginning, all talked a lot about editing and the power that StyleGAN provides us for performing these edits on real images. So let's take a step back and look at PSP and how we can try to edit images using the latent representations that that PSP provides us. So here we have the original image and the inversion that PSP has given us. But when I go to edit the inversion, we get the following results. And we can see that there's a bunch of different artifacts here, especially with the pose and the age edits. And I feel that we can do much better than this. So we asked ourselves, we kind of took a step back and asked ourselves, why is PSP so great at inverting and performing these awesome image-to-image translations? But when we go to edit the latents, we get some pretty, unsatisfying results. So let's just try to go through our thought process here in analyzing this gap. And when we talked about StyleGAN, we said that it has this W latent space that tries to model the true data distribution that StyleGAN was trained on. And using this W latent space, we're able to generate images of exceptional quality. But now, when I introduce PSP into the picture, and I ask it to encode this image that we see here on the left, nothing is telling PSP how to encode the image into latent space or where to encode it into this space. So rather than encoding it into these well-behaved regions of StyleGAN, it could very well be that PSP will choose to invert the image into this yellow dot that we see here in this W plus latent space. And who's to say that this region of W plus is well-behaved? Who's to say that I can perform these semantic edits within this gray region over here? So this leads us to this trade-off between something called distortion and editability. So what do I mean by this? If we look at optimization into W+, and we look at the reconstruction that we get, we're able to get near perfect reconstructions of Messi. But when I go to edit its latent representation and say change the Messi's age, we can see that the results leave some artifacts. For example, in the young edit over here in the middle, we can see that it's not able to completely remove Messi's beard. Now, using an encoder that's called Encoder for Editing, another work coming out of our lab at Tel Aviv University, E4E is actually trained to encode images into well-behaved regions of StyleGAN, these so-called good regions of StyleGAN. And we can see now that the edits are quite amazing, right? Both the young and the old provide us with high quality edited images. But if I look at the reconstruction, we can see that this individual is clearly not Messi. Right, so we have this trade-off between distortion, how well I'm able to reconstruct our original image, and editability, how meaningful are these latent codes, how editable, how many edits or how meaningful are the edits that I perform. And this leads us to, another issue with optimization. If we take a look at this image over here on the right of this individual with this painted face, we can see that StyleGAN was never saw this sort of image during its training, right? This isn't part of the FFHQ dataset. It's quite out of domain to what StyleGAN has seen. And if I go to perform optimization to try to reconstruct this image, we'll get the following result. We can see that we're able to capture the structure of the individual's face, but we're not able to capture that paint on his face. So it seems like with latent vector optimization, we're not able to capture these out-of-domain images. So what can we do? This leads us to another work coming out of our lab called PTI, Pivotal Tuning for Latent-Based Editing of Real Images, where here we're actually going to make two different changes to the latent vector optimization that we just saw. First, we're going to start with a latent code in W rather than W+. And this is important because it will make sure that we're going to be able to perform high quality edits on the resulting inversion. And second, when we perform the optimization, rather than updating the latent code, we're going to update the StyleGAN generator itself. And by doing this, by performing this optimization and changing the weights of the StyleGAN generator itself, we're able to kind of shift StyleGAN in order to capture our input image, even when it's out of domain. Now notice now that we're able to capture that paint on the individual's face. So now, because we're using W instead of W+, we'll get high editability like we want. And now we're able to capture these out-of-domain challenging images that StyleGAN has never seen before. But the problem, because it's optimization, is that it's slow. It takes about a minute per image. So it's not very scalable for interactive applications, which at the end of the day is quite important for us. And let us recap where we are when we're talking about inversion methodologies. We started talking about optimization and encoders, and we can split these into now two sections, having a fixed generator and performing optimization on a latent vector, or using encoders such as PSP and E4E and Restyle. But here the generator is of course fixed. And just like we just saw in the last slide, we have PTI, where we're going to perform an optimization to tune the generator in order to get these higher quality reconstructions. But the question is, what goes on over here on the bottom right? Is it possible to design an encoder-based technique to learn to tune the generator itself. And this leads us to our next work called Hyperstyle, which was published in December of last year, where we're going to ask ourselves this question, how can we tune a generator without performing optimization? And the answer to this, the answer that we found, was with hypernetworks. For those of you who don't know what hypernetworks are, it's a network that generates the weights for a different network, which in our case is StyleGAN. So how does this look? Given some input image that we see here, we're going to start with some initial latent code called winit within W. And our goal is to learn to modify a pre-trained StyleGAN generator to obtain a new generator that leads to a better reconstruction of the input. So how do we do this? How do we find a modified generator using a hypernetwork? So we'll get to that in just a second. But here, if we take this initial latent code, our goal is to take this generator, modify it a bit, modify the generator's convolutional weights, but now pass the same latent code that we just saw in order to obtain a much more accurate reconstruction, right? So our goal is to transform this initial reconstruction that we see here in the middle to obtain the final reconstruction that we see here on the right in order to reconstruct the input that we see on the left. So how do we design this hypernetwork? We'll take our input image, an initial reconstruction that corresponds to the latent code winit, and pass it to pass both images like we did with Restyle to our ResNet backbone to obtain a shared feature map, of size 16 by 16. And this is where the hypernetwork comes into play. We're going to have a set of refinement blocks. Okay, what is each refinement block? Each refinement block is actually tasked with learning to modify the pre-trained generator weights. So for example, in this top refinement block over here, we can see that we have an output of size 3 by 3 by 512 by 512. And this means that we have a convolutional layers of where the kernels, the filters themselves, are of 3 by 3, that's the spatial dimension, each with 512 channels, and we have 512 such filters. Okay, so how does this look when we combine it with StyleGAN itself? We're going to shift these refinement blocks over here, and this is the architecture of StyleGAN. What we're going to do is each refinement block's output is going to correspond to a single convolutional layer of StyleGAN, and we're going to change these convolutional filters themselves, the actual weights of StyleGAN. Right? And we're going to do this for each of the different layers of StyleGAN. Now, what's the problem with this scheme? As you may have thought, quite a lot of parameters. Designing such a hypernetwork requires over 3 billion parameters. We're talking about the size of GPT-3 over here, right? So it's not very scalable, right? And we don't have the enough hardware to train this hypernetwork. So we actually made a few modifications to the network itself in order to make it more practical. First, we shared weights between different refinement blocks. A lot of these refinement blocks share the same output dimension. So there's no reason not to share their weights between these different layers. And this gives us the added bonus that we have information sharing. So using these shared weights, we're able to decrease the generator's, the hypernetwork size from 3 billion parameters to about 1.4 billion, about half the size, which is quite good, but not good enough. So in addition, what we're going to do is we're actually going to compute an offset per channel. We have this 3 by 3 convolutional filter. Rather than computing an offset for each of the 9 parameters, we're going to output a single offset for the entire channel. And this reduces the number of parameters from 1.4 billion to about 330 million. And just to give you an estimate of where we are in comparison to PSP, PSP had about 270 million parameters. So it's still quite a bit higher than PSP, but something that we can definitely work with. So we have these refinement blocks. How do we, get our modified generator? We're going to simply take the outputs of the refinement blocks, pass them through our pre-trained generator to obtain our modified generator by simply adding these offsets to the weights, to the convolutional weights of our original generator. And now, if we pass our initial latent code winit in W, we'll get our final output image that we're looking for. And by the way, we talked about how with PSP, it was kind of hard to invert the image in a single pass through the network. Here, you can think about it that it's quite hard to compute the desired offsets in a single pass through the hypernetwork. So what we can do is we can apply the same iterative refinement scheme of restyle, but rather than applying it on the latent code itself, we can apply it on the weight offsets that are predicted by the hypernetworks. And this allows us to gradually refine the predicted offsets of the hypernetwork. And we found that by doing so, we're able to get much higher quality reconstructions with fewer artifacts. So let's see some of the results of hyperstyle. And just to give us, to understand where we are in comparison to previous works, if we take a look at PSP, which we know was published just a year and a half ago, it's kind of amazing to see the progress that we've made in the world of inversion. Right, we're able to better capture, for example, James Harden's beard or Brad Pitt's hair that we see here on the right. Right, so pretty impressive things. And hyperstyle, the inference time for hyperstyle is about still less than a second per image. So we're still in that range of the interactive applications that we're looking for. And a lot of the focus of today was performing these inversions, but also being editable, right? And with hyperstyle, because we're staying in this W latent space that's well behaved, we can edit realistic images, get high quality reconstructions, while also performing these amazing edits that we see here of Leonardo DiCaprio and Alison Brie, changing things such as hairstyle, adding facial hair, changing lipstick and expression. And the question is, what about out-of-domain images? We saw that PTI is able to handle this by tuning the StyleGAN generator. Can the same thing apply with hyperstyle? And just to show you that encoding out-of-domain images, with encoders is not really possible, right? Here's an image, a cartoon from the show called Archer. And we can see here on the right that we actually get a sort of realistic version of the cartoon, which is quite cool, but it's not really what we're looking for here. We're actually trying here to reconstruct the cartoon itself. Now with hyperstyle, we actually think about it that we're going to extend the latent space of StyleGAN. So now if we get a cartoon image, we're going to kind of be able to more accurately encode it, even when the image was unobserved, both for the StyleGAN and for the hyperstyle encoder. And now, since we're able to kind of extend the latent space of StyleGAN, kind of inject the cartoon into its latent space, we're able to get a much more accurate, much more faithful reconstruction of the cartoon. And as you can see here, the reconstruction itself is not perfect, right? There's still a bit of artifacts, but it's still quite nice to see that we're able to improve over standard encoders. And a few more results of encoding paintings and animations and things like that. White Walkers even, so pretty cool things. And this ability to encode these animations and paintings allows us to, of course, perform edits on these animations, which is quite nice to see.
Thanks, Yuval, for explaining the difficult parts. Let's go to the fun part of the presentation. We're now going to talk about 3 applications that we're able to do with StyleGAN. Let's start with the aging task. In this work, which was accepted to SIGGRAPH last year, we showed how we can model the human aging process using StyleGAN and encoders without requiring any paired data. Observe the high-quality images and the disentangled edits. We're able to change the age without affecting the identity or any other attribute. So how do we do so? With SAM, our proposed approach, we're going to start with a pre-trained PSP encoder to get our initial inversion of the input image. Now we're going to introduce another encoder called eAge, which gets as input our image X and the desired target age alpha T. This encoder eAge is tasked with outputting some latent representation, encoding the input image and the desired age. If we take our PSP encoding and the output of eAge and sum them up, we get our unified representation. Finally, passing this into a fixed pre-trained StyleGAN gives us the output image of the person at the target age. To train the encoder, we utilize a pre-trained age classifier, which guides the age transformation. By using the age classifier, we alleviate the need of having paired data. Another advantage of SAM is fine-grained control over the result age. By viewing the aging process as a regression task, we can get accurate age transformation, unlike other latent traversal methods. Where did the disentanglement of SAM come from? Since we train an encoder, we assume nothing about the nature of the path in the latent space. This allows SAM to learn nonlinear passes which disentangle the age from other attributes. The paths that you see here are the actual passes learned by SAM. We'll now talk about two another works in which we pair StyleGAN with CLIP, the vision language model. For those of you who are not familiar with CLIP, CLIP provides an image encoder and a text encoder. These encoders were trained to map image and corresponding text into a common latent space. We'll start by talking about StyleClip. In StyleClip, we employ CLIP to guide a traversal in the latent space. This allows us to use text for editing images. We introduced three approaches for employing CLIP in the latent space navigation. Each of them has pros and cons. Since we're short in time, we will focus on the global directions approach. The goal is to find a global direction in style space such that by traversing along this direction, the target attribute is modified for an arbitrary image. For example, here we show the global direction of gray hair. Note that for the three examples, the same direction is applied, and that is why we refer to it as a global direction. And here is another example where the global direction is for the prompt happy dog. We will now see how to construct a direction delta S given a text prompt. But first, let me explain about the relation between style space and clip space. A direction in style space, denoted by delta S, has a corresponding direction in clip space, denoted by delta I. We find delta I by applying the image encoder to a pair of before and after images. Now, this direction should agree with the direction in clip space defined by the text and denoted by delta T. So we use the two text prompts to define a direction in clip space. For example, here we use a photo of a face and a photo of a smiling face. So we started with a direction in style space and transformed it into a direction in clip's text space. Now we can go in the opposite direction. We can start with the target text prompt. We can then construct a perf prompt which corresponds to a text direction in clip space, and then we can construct a matching direction in style space. This direction in style space consists of 9,088 dimensions, which is the number of channels in style space. So for each channel, we measure how much the direction of that channel in clip space is parallel to the text direction. More specifically, I will now explain the process for each channel. For channel C, we perturb it, generate the images before and after the perturbation, and then encode them using clip. This gives us a direction in clip denoted by delta IC. Then we take the target direction, delta T, and measure the inner product between these two directions. This gives us the relevance of channel C to the target direction. The relevance is the scalar beta C. Now, if this beta C is larger than some threshold beta, then on channel C of the direction in S, we put beta C. Otherwise, we put 0. And we call beta C the disentanglement parameter. And here are some results. Here you can see traversal along the direction corresponding to the target text, which is written below the images. We can change the hairstyle of Hillary Clinton into curly, high top fade, fringe, black, and we can even add her makeup. Observe the high disentanglement of the edits. And here are more results on dogs. We can make it happy, we can make its eyes bigger, change its fur color, or change its breed. And here are more examples of car manipulations. We can turn the car into a Jeep, into a sport car, into a car from the 60s, and even to a classic car. Now, let's talk a bit about the limitations of StyleClip. Since we're editing in the latent space of StyleGAN, we're limited to images within its domain. But what if we would like to take this image of Brad Pitt and make it look like a Botero painting, or a zombie, or even a Pixar character? This is not possible using StyleClip because these images are outside of the domain of StyleGAN. This brings us to the next work that I'm going to talk about, StyleGAN. The key idea in StyleGAN is to shift the latent space of the original generator. So we can shift the latent space toward pixel images or toward zombies. The shifting is guided by clip only, so the generator never sees an image from these target domains. So we actually do a zero-shot domain adaptation. A simple idea to perform this domain adaptation is to optimize the generator weights with the guidance of clip. We can fine-tune the generator with a clip loss that encourages the generator to output images corresponding to some text. For example, here, we're trying to shift the domain of dogs generator towards cats generator. Sounds simple, right? But it doesn't really work. We get images like this one or this one if we keep training. So where did we go wrong? Let's visualize clip's latent space. These are the encoded dog images. These are the cat images. This is the embedding of the text dog, and this is the embedding of the text cat. When we optimize the generator, what we actually did is to take all these dog images and tell them to move towards the embedding of the text cat. When this is our training goal, the GAN has no need to maintain any form of diversity. And when we lose diversity, it's also much easier to come up with adversarial noise that fools clip. And indeed, we can visualize our generated cats and see that they all reside in a small area. So instead, in StyleGAN Nada, we work with directions. Similarly to the global directions approach of StyleClip, we're looking at direction in clip space and demand them to be parallel to the direction defined by the source and target text prompts. For example, here the target direction is from the embedding of the text dog to the embedding of the text cat. And now, as you can see, the generated cats reside on a much larger area, and the generated cats looks much better. Okay, so we've talked about the training goal, and for that, we're going to need to find directions between pairs of images generated with the original and the new generator. So how do we do that? So we just use two generators. We'll start with the two generators initialized to the same model. Let's say the one that produces faces. Since they are started out the same, if we feed the same latent code into both models, we're going to get the same image. Now, the stop generator is going to be kept frozen. It's not going to change throughout the entire process, and its only job is to provide us with some context for the direction loss. The second generator gets trained. And where do the gradients come from? We put the images produced by the two generators into clip and calculate the direction between them. Then we demand that this direction is parallel to the direction described by the text. For example, here, the direction from a photo to an anime painting. And we can use the gradients to modify the generator itself. And that's it. We now have an anime painting. Now, keep in mind that we aren't just editing a single image. This is an entirely new generator that produces anime paintings. So just to convince you that we have trained a new generator, here we have nine new generators, and we apply editings in their latent space. Observe the diversity of possible generators we can obtain, and keep in mind that the generator has never seen a single image from these domains. And with that, I want to thank you all. I invite you guys to check out all the project pages, and thank you again for listening.
So thank you everyone for coming. So my name is Ivan Aguilar. I'm the chair for the AI and VFX track, and I'll be moderating the session. So we'll now have a Q&A for the talk called StyleGAN for image editing and manipulation. So this talk, it explored the use of StyleGAN and its recent techniques and the advancements that it has in inversion for GAN inversion and the importance that it has for real image editing applications. So we have two speakers, Yuval and Or. They're both graduate students at the Tel Aviv University, and they gave the talk, and we're going to be having a talk with them. So before we begin, so here on Zoom, you can post either in the chat, or there's also a Q&A feature, and you can ask any questions that you have for them, for their talk at any moment, and then I'll ask them the questions. Okay, so So to start things off, I have some questions. So is it possible to use, first of all, thank you for the talk, right? Everything that you guys talked about is really interesting. And the first question I have is it possible to use StyleGAN to generate images in people in different lightings or in different weather conditions? So for instance, if you were to change the angle of the sunlight, or if it was in a raining environment, right, the hair would be damp, or if there was windy, there will be wind blowing in the hair. And normally the examples you all gave, everything was kind of static. I know it's static, but everything was, right, there weren't any of these conditions. But so is this possible, or is this one still an open question?
So I think that in a work that called the style flow, there is a possibility to change the light and I'm not sure about the weather, but the direction of the light. Similarly to things that we showed, they find paths in the latent space that corresponds to these changes.
Yeah, I think it's also still a very open question how to get the that more fine-grained control. Like right now, we know how to make these different manipulations of like age and pose and things like that. But the things that you mentioned, making the hair damp and things like that, that's really like fine-grained control and precise like manipulation on the images. I think that's a very interesting and very useful application. But I don't, from what I know, I don't think there's any works that have really gone to that level of detail. So definitely an interesting question for the future.
And then, so when you were showing all the examples, so normally they were all static images, right? So you showed how an image could change and how the effects. Would this also be possible for animations, or could you generate a series of images that have subtle changes that you can combine to create an animation?
Yeah, so there are a bunch of different works that from when StyleGAN first came out, most people worked on still images. I think in the past couple of months we've seen a shift towards more of video editing, video generation with StyleGAN based methods, and there you have a lot more different challenges that arise with one of the things of making the animation smooth. Right? Because if I, for example, edit one of the frames of the video, independently, you get these like jittering and you get an inconsistency between the frames. So there are a bunch of different works also coming out of our lab from Tel Aviv that are trying to get into that world of video editing and try to overcome those different challenges with videos.
Okay, great. And one thing I was curious about is how do you measure the quality of the results? So whenever you go through the whole process and you have the generated image at the end, how do you assess if it was good or not only just by looking at it?
So I think this is a really open question. It's generally it's very hard to assess the quality of generated images, and maybe it's even harder to evaluate edits. Some approaches include measuring the FID, which is supposed to measure the quality of the image, and to measure edits, to evaluate edits, you can use a pre-trained classifier to check whether the intended edit was done, but it's generally a really open question. And for some edits, you don't have a classifier that can help you with that.
Yeah, I think one of the interesting, the challenges, most of our works we focus on faces, right? I think that's the most interesting domain to work with. And, one of the most important things is to, when you make an edit, to preserve the identity of the person, right? Because if I have an image of, let's say, Obama, and I edit it, but it doesn't preserve his identity, then it's kind of meaningless, the manipulations I perform. So a lot of the metrics that we use that other works also use is to compare the identity of the original image and the identity after the edit to make sure that it still resembles the same individual.
Mm-hmm. And then, so as you were saying, so how do you do that comparison exactly to see if it does resemble?
Yeah, so with a pre-trained network that was trained for a face identification.
Yeah.
Oh, okay. And then have you ever seen any works where, especially on editing, where the comparison is with somebody who's an artist that tried to do the same edit? Has anybody done anything like that, where you have StyleGAN to do an edit, but then you have an artist to do the same edit and then try to see if it's similar?
Yeah, that's an interesting approach. I don't know any works that do that. I think the reason why I guess I haven't seen something like this is because it takes it's quite labor intensive to get large scale data sets of edits that an individual has made. But it's something very interesting. I never thought about it actually. Yeah.
Yeah, me too.
Okay, next question. So machine learning is sometimes kind of like a black box. So especially when you think about what you want out of it, what you're trying to get out, you don't really know too many information of all the convolutions, everything that's happening in the middle. So you touched a little bit about this at the very end. I wanted to know what are your thoughts on of using these tools, but also having room for user feedback. So user will start giving some input on what things they want to change, or maybe even during the process, or once the final image is generated, right? What we'd like to change based on that.
So I think that generally one of the things that I really like about StyleGAN is that we have a lot of intuition about how it works. Specifically about this feedback idea, I think it's a very interesting idea. I haven't seen such an approach, but maybe it's a direction that's worth thinking about, because again, I think that in StyleGAN we have a lot of intuition about what's happening in its latent space.
Yeah, because I think that would be very interesting. Thinking of it more as a tool for artists. So once you have generated an image, like, oh, you generated this hair on this character. Now I want to change its color or change the style or tweak it, because then it starts becoming a tool that can be used for film or for animation.
Yeah, there are works that allows the user to specify the regions that he wants to edit, and so such maybe in the sense of spatial control, there are such approaches, but generally not a lot of works with user feedback.
So you also mentioned that, if I'm not mistaken, for StyleGAN, it uses the FFHQ database for the training. Do you know if this database can be modified? So for example, if a studio or somebody wanted to do their own training, can they add images to it and do the coding, do the labeling, and then retrain it? And if so, do you know how long it takes to train?
Yeah. So with FFHQ, you can definitely, I think with any machine learning model, more data is better, right? So we have with FFHQ, there's 70,000 images, but the more images you add, the more diverse images you add, then the more powerful the model will be. So typically, yes, for when we write papers and publish works and things like that, we use standard data sets. But if you're trying to build a real world application, then adding more data is typically going to help. And what's nice with StyleGAN is you don't need to label. Typically, you don't need to label the images, right, to get the more powerful generator. So pretty much the more data, the better in this case.
So I guess can you just touch a little bit more on why wouldn't you need to label? Because I know a lot of other ones you might need to.
Yeah. So how StyleGAN works is really we're trying to learn. We have a distribution of images. We have a collection of images, and we're trying to train a generator to output images that match this distribution of real images, right? So if we have a wider set of data, we have a wider data set, then we're going to train the generator to better match this wider distribution of images, right? There's no labels there's no need to learn labels. We're just trying to match the outputs of the generator to match the distribution of the real images.
Yeah, that's very interesting. That's the difference.
Yeah.
So from what you guys have worked on from the past years and what you've seen, have you seen any software that uses StyleGAN or uses any of these techniques embedded, like any image editing software or 3D modeling software?
So I know there's a bunch of different people who are trying to get into this world for, say, I want to build an application for image editing or things like that. Many people are starting to have reached out to us also to discuss ways that they can incorporate our works into their systems. But I think there's still a lot of challenges in transforming, these works to work in real world scenarios, because there you have a bunch of different edge cases that you have to handle. And, there are, I guess, consequences to every action that you have in a real world application. So, it's starting to shift into that direction, but there's still a lot of work to be done, in my opinion.
Yeah, I agree with Yuval. I think there are a few companies that are already that have already adapted these techniques for more simple cases, like Yuval mentioned. But yeah.
And I guess a little bit different question. What are there any ethical concerns that you guys think of when, especially for editing images of people's faces, that you guys think of when you're doing this work?
Yeah. So I guess whenever you're talking about image generation, image manipulation, the first thing that maybe pops into your mind is the world of deepfakes and things like that. And I want to think that most people that use StyleGAN and use related works are trying to do this for a good purpose. And there is the growth of the world of deepfakes and things like that. But at the same time, there's also a bunch of different works that are working to detect GAN generated images and deepfakes and things like that. So there are ethical concerns, but I think most of the work that people do when they work with StyleGAN is for good positive use.
And are there any tools that are used today to be able to identify if something has been edited, either for deepfakes or any image editing?
Yes. So there are a bunch of, I don't know any specific works that try to detect GAN generated images. But one of the works that I remember is that trying to look at the eyes of the generated images, or the fine details, because GANs aren't precise enough to get the eyes perfectly circular, and then you can detect fake images that way. It's a bunch of different tricks like along those lines to try to detect those fake images.
Okay. And I guess another question is, for those that are still trying to get into the field of machine learning, that are still want to get into the field, maybe they haven't done anything yet, what do you recommend? Where can they start learning, or where would be a first good place for them to get into this?
So I think it's very important to both read papers and be updated, because there are a lot of works that are published on time, and at the same time, I think it's very important to to do a hands-on training or something like that. For me, it makes things much easier when I just look at the code and start playing with stuff. And I think there are great courses at the internet, so that's how I got into this field.
And if I could just add, I would also, how I always tell people who want to get into the world of research, find a paper that interests you, find a topic that interests you, and hopefully they have code, and try to break their method, find cases where it fails, and then see how you can think about solutions that we can help solve where they fail. And that's how we get this progress, very quick progress in this field, trying to see where people fail and find approaches to fix those gaps along the way.
Thank you very much. So I think that's all the questions we have for today. And I wanted to thank you both for the time that you took to make the presentation, and also for coming for the Q&A. Thank you very much for that. Is there anything last that you guys want to say before we close?
Thank you for the invitation.
It was really, really fun to be here and talk with you. And we had a really fun time making the presentation as well.
I'm glad. So thank you, everyone for watching, for coming. And if you haven't seen their talk yet, please go and watch it, and watch the other talks that we have. And also stay tuned for the other Q&A sessions that we'll have for the rest of the day. So thank you all for coming, and have a good rest of your day.
Thank you.
Bye, everyone.
Bye.